Okay, so welcome back to Particle Physics and a Standard Model. This is lecture 27. And last time we wanted to understand a statement that I had made a couple of lectures ago, that spinors in quantum field theory are nothing but yet another representation of the Lorentz group. And on the way to seeing that, we first solved the Dirac equation and found that you could write the propagating degrees of freedom in terms of these two spinors that can be represented as 2 cross 1 column matrices, correct? And then we started exploring the Lorentz group in its usual the regular representation that you would have seen before, the 4 vector representation, right? And we saw that the Lorentz group comprises of not just boosts but also rotations, right? And from there we went on to the concept of Lie groups, that are continuous groups containing infinite elements generated by a finite number of generators, in this case generators of rotations and boosts. Agreed? So these generators generate the entire group, hence their name. And from there we went on to the concept of the Lie algebra, which is basically an algebra that the generators themselves live in, and the multiplication rule is called the Lie bracket. And we saw that the Lie bracket for the Lorentz group was this, that the commutators of the rotation generators give you back a rotation generator with an antisymmetric Levi-Civita tensor, but somewhat surprisingly, when you commute the rotation generator with the boost generator, you get back a boost, and then when you commute 2 boosts, you get a rotation generator, right? So boosts and rotations are inextricable from each other. If you do not remember this from special relativity, go back and refresh your memory on this, okay? So you can't have one without the other. Good. Now all that will now come into play when we want to understand the spinor representation of the Lorentz group, okay. So let me define, okay, a combination of the boosts and the rotations, which I am going to call some n, okay, and I am going to label the I, the spatial component, and the combination I am going to take is just Ji plus Iki, okay, and then I am going to normalize it suitably because something amazing is going to happen with this combination. And just for fun, I am going to call this combination R. If I write this combination, I can always think of some orthogonal combination, correct? And that is this, right? So what shall I call this combination? I can call it L, suggestively, okay. Why would I call this R and L? It comes down to whether I put a plus or minus in front of the boosts, right? It seems like over here I am boosting in a certain direction and over here I am boosting in another direction, correct? Might as well call them right and left, that is why I have R and L, okay. So what good can come out of this combination? Let us inspect what these commutators would give you. If I take, there are 3 combinations of commutators I can think of, right? RR, LL and RL. So let us see what happens, okay. If I take the right handed generators, these are still generators, right, because I have just combined 2 generators and they live on an algebra, so I can just add the generators, no problem, right. What do I get here? Take a look at this set and write it down. So the J and the J commute, the J and the Ji and the Ja will give you a Jk with an epsilon ijk, and then what happens? The J and the K give you a K, right, but then that is a cross term that you will get rid of, and then the K and the K give you another J, right, okay. So go ahead and do this. This is an exercise for you. You're going to find that you're going to end up with the epsilon ijk goes for a ride, but you're going to end up with once again the generator NKRG, okay, the right handed generator. Similarly, no surprise, this so called left handed generator is going to give me epsilon ijk NKL. Okay. Now can you guess what happens if I combine the L and the J? Again, go and do this yourself. If I combine this, okay, of course that's also this, left and the right, that's just 0. Okay. Now these 3 commutators have a very deep interpretation. Okay. So what has happened here? This looks just like the rotation algebra, correct? The right handed ones are independently in their own rotation algebra. The left handed ones are independently in their own rotation algebra, correct? And in case you didn't think they were independent, if you try to mix them up, you get a 0, just to show you that they are indeed independent, correct? In other words, the Lorentz group, right, that we started out with, right, in the 4 vector representation, seems to contain actually, by just slightly manipulating the rotation and boost generators, by putting them in a certain combination, they seem to contain that Lorentz group seems to contain, right, 2 commuting sub-algebrae. I don't know if it's algebras or algebrae, let's just put algebrae, right, that mimic 3D rotations. They are not really rotations, okay. So let me say mimic. It's not really a rotation. This is the real rotation, but the algebra seems to look like rotation, right? Okay. Now that tells you that the group, it seems like we've broken down the Lorentz group, okay, into, let me first write it this way, then I'll write the correct way to write it, okay. We seem to have broken down into 2 SO3 groups, okay. SO3, I'm going to put that in quotes, but no, it's not really SO3. Why? Because, you know, I have a J, I mean I have an I sitting here, right, Ji plus I Ki. So this is not a, these are not real generators, correct? So if it's not SO3, what could it be? Remember when we dealt with spinors in quantum mechanics, we said that the spinors, you know, the 2 spinors in quantum mechanics now, right, when we did rotations on them, right, we had to apply a 2 by 2 matrix, and that 2 by 2 matrix turned out to be unitary, correct? And then we said that the spinor rotation, right, happened, those transformations happen in an SU2 group that represents rotations in real space, correct? All those rotation matrices comprised of 2 by 2 unitary matrices, right, that also had determinant 1 with determinant of U1. Remember all this? That's what this is again, okay. And remember that the SU2 algebra also looks like this, right? Take the Pauli matrices and see for yourself that it also looks like this, right? This is exactly why the spin angular momentum is called that, because it looks like the regular orbital angular momentum, which represents real rotations, right? Okay. So what I am trying to say here is that this is not actually broken down to two SO3s, it is the cousin of SO3. Remember SO3 I once wrote, it is like SU2, right? Or I can even write it with capital letters which actually represent the groups, right? So what I should be actually writing is that the SO13, okay, now I am going to write it in technical notation, is made up of two SU2s, okay, but this is not the usual breaking down that we think of. This is not some reducible representation or anything like that, okay. This is a direct product of two SU2s, okay. If I had put a plus here instead of an X mark, that would mean that I have broken this down into two reducible representations, two blocks, right. If you take a matrix, if I can break it down into block matrices inside, that is a reducible representation. That is not what we have done here, okay. When we started constructing the Procol-Lagrangian, if you go back to that lecture, remember we broke down the Lorentz group into 4 scalars, right, 1 plus 1 plus 1 plus 1, and similarly when we went for the correct equation, again we broke it down into 1 plus 3 and then we got rid of the 1, right. We are not doing anything like that. We are literally re-representing the Lorentz group without losing anything. We just changed the generators, okay, we just rephrased the generators, and so this is literally made up of these two groups. You can always break down a larger, not a breakdown, you can always write a larger group as a direct product like this of two other groups, okay, just shows that these two are independent. I can go further and distinguish between this group and this group, okay. Might as well give them the label L and R. The L stands for boosts in some direction, which I am going to call left handed, the minus I am going to give left handed, the R stands for right handed. If you want, you can just call them plus or minus, okay, if you do not like left and right, does not matter what you call them, but left and right turns out to be a useful way to think about this for at least this course, the standard model, okay. Okay. What have we learnt here? That the left and the right handed representations are both independent, okay, completely independent representations of the Lorentz group, just like 4 vectors were and just like scalars were, okay. And indeed that is what we mean by spinors, okay. And in particular when we talk about these 2 cross 1 spinors, there are a few names for these. I just like to call them 2 spinors, okay, but they are also called Weil spinors. Some people just call them 2 component spinors and so on, to distinguish them from the 4 spinors or the 4 component spinors or the Weil or the Dirac spinors, okay. Let me just write that 4 cross 1 that we started out with, they are the 4 spinors or the Dirac spinors, okay. Can we see now that what is more fundamental are the 2 spinors? You can construct Dirac spinors by putting a couple of 2 spinors in them. That is exactly what we are seeing here, right. So of course sometimes you also have things called Majorana spinors, also made with 2 spinors only, okay. These are all 4 cross 1 spinors, these are all 4 spinors, which is an artificial construct. I'll just write it because it's important. An artificial construct, okay. So What have we learned here? That spinors are nothing but yet another independent representation of the Lorentz group. In fact, this is the smallest non-trivial representation of the Lorentz group. Okay? If you forget everything else in this course, don't forget this, that spinors which describe fermions that make up matter are nothing but yet another representation of the Lorentz group. And that is of course different from what we call spinors in quantum mechanics, right, where that is just something transforming under rotations. It is just something that you use to represent spin states so that you can see how they transform under rotations. But here it is not just rotations, rotations and boosts are together here. We are thinking about the complete Lorentz picture, relativistic picture, right. Okay. So now in this light we can understand all the other representations that we know of in the Lorentz group. For instance, let me go to a new page. Okay. In this light, okay, let me once again rewrite this. This is SU2 cross SU2 left right, correct. So now if I want to write, because I can charge states in both the left and the right one, right. So if I want to write a scalar, what do? I just say that it is a singlet under both the left and the right, okay. It is a singlet under SO13 entirely, but now I have to write it differently. So for a singlet I am going to represent it with a 0, should be an intuitive notation, right. So that is what I would call a scalar. What is the next smallest representation? I charge something under the left handed one but not the right handed one, okay. And again this should be an intuitive notation from considerations of spin, right. So I can say this is it carries a spin of half, so to speak, or they represent the group. The representation itself can be written as a half, okay, and that is a left handed Weil spinor, okay. What is another equivalent I can write? I can of course write a right handed Weil spinor. Correct. Now what about vectors? How do I represent a vector now? For that I need to charge both of them, right. That is the next non-trivial representation. So if I charge both of them, we know that vectors, they can have both left and right circular polarization, right. So that is what I am representing here, okay. They need to have both polarization, they need to be charged under both the left and the right handed ones, they behave similarly under boosts basically, right. And finally I can go to higher dimensional representations. What is this? This would represent a symmetric traceless tensor. Okay, what is that called? What is the only symmetric traceless tensor field that we know of? This is not something that we particularly learn in this course, but that is nothing but the graviton, the quantized mediator of the gravitational force. Okay, is that good? So with that in mind, we can now understand some of the observations we made about the Dirac equation and how the four spinors break up into two spinors and so on. Okay. So now that would involve going back to the Dirac equation and trying to guess what really is the Lagrangian for that. Okay? Remember, this is a Dirac equation. So what could be the Lagrangian? So once again, this comes down to the art of writing down Lagrangians. You will see that, let me say Dirac Lagrangian is, I am going to write this in the full notation. So psi dagger gamma naught, okay, I gamma mu partial mu minus m psi. Okay, notice the gamma naught here. Out of nowhere I have put this in, right? This doesn't look like anything that we see in the other Lagrangians, right? The Klein-Gordon or the Proca Lagrangian, correct? But you do need the gamma naught, okay? Without the gamma naught, it turns out you cannot construct a Lorentz invariant Lagrangian, okay? I refer you to any number of textbooks, but take for example Schwartz, okay, Schwartz's QFT textbook, where you can see that when spinors are involved, you need the gamma naught to get Lorentz invariance in the Lagrangian. Okay. So sometimes people, in fact most times, people write this as, this becomes a little confusing if you are not used to it. They put a psi bar. Okay. Psi bar is nothing but psi dagger gamma 0. I think I have been putting the gamma, the indices for the gammas upstairs. So sometimes I put downstairs, but you have to remember you should always put it upstairs. Okay. So what does this mean? If psi is written as psi a psi b, then psi bar is what? Because gamma naught contains identities in the off diagonal places, right? Then this just becomes that. Agreed? Okay, good. So now we are going to expand this into two spinors, because that's when we'll really see what the physics is. Okay, so I'm going to expand using remember this in the while basis that we are using, right, where this is nothing but the 2 by 2 identity matrix and the Pauli matrices, and when I have a bar, that's nothing but again the identity matrix with the minus for the Pauli matrices. Okay, this is a shorthand notation. So we can now use this in the Dirac Lagrangian, and I am going to expand this in terms of two spinors, which I can do because these are all in block diagonal form, right? That is the beauty of this. So I am now going to rewrite the Lagrangian. Let me write this in a new page because it is an important expansion. Okay. So the Lagrangian in two spinor form is using psi a and psi b only as my two spinors. It is, first of all, you will get this, okay. The psi a and the psi a are thankfully in the same term, and this is indeed the kinetic term, right. It has a derivative, correct. So this is what gives you the momentum of the field in the equation of motion, and similarly this psi b also independently picks up its own kinetic term. Okay. See, already you can see here, right, that the mu's are actually contracting with each other, and that only happened when you had the gamma naught. Okay, so you can already see. So you can go to look at Schwartz's book also, but here itself you can see that to get Lorentz invariant kinetic terms at least, you needed the indices to contract, and that's what's happening. Okay, and also the psi A marries the psi A and the psi B marries the psi B, right. All of this is ensured by having the gamma naught. Okay. And then what am I missing? I am missing the mass term, right. That is where things become crucial. See what happens to the mass term. Okay. So I now have once again the gamma 0 flipping things around in such a way that because they got flipped around, and since there is no other gamma matrix in between, the psi A actually gets married to a psi B and vice versa. Okay. So although this is in the left handed representation, so we will come to that. These are obviously these are in completely two different representations, and yet they have married each other to give a mass to the spinors. Okay. So the first observation here is that it's no coincidence, okay, that these two have separated out in this way in the kinetic term. Okay. Why? Because indeed psi A and psi B are Weil spinors which are independent representations, right, of the Lorentz group. That is, psi A is what I would call psi L, which lives in the left handed SU2. Remember from here, left handed SU2, and psi B is what one might call psi R because it lives in the right handed representation of SU2. Okay. So I could have just written psi L and psi R to begin with, but because we use the older notation, that is what I went with, right. Okay. Now here is another thing. Okay. See the mass, right, the mass basically what is the mass term doing? It is marrying of a left handed and a right handed field now, right. Here it is a right handed and a left handed field, right. Suppose I take the mass to 0, okay, if the mass is 0, right, then does not it look now like you can have two independent Lagrangians, right. I can write a Lagrangian just for the left handed fields. Okay, let me just write it very quickly, okay, so that there is no ambiguity. This is the Lagrangian for just the left handed field, and then I can have a Lagrangian for just the right handed field, right. I just replace left with right here, right. In other words, I can have independent theories for left and right handed if the mass is 0. Okay. This kind of behavior is exactly what is known as a chiral theory. Okay. Why chiral? Chiral means hand. So one hand is independent of the other hand in this case. Okay. So what is one consequence of this? If the fermions have no mass, okay, suppose I am working in a theory where the fermions have no mass, since the left and the right handed spinors are independent, it is completely up to me to charge the left handed states and not charge the right handed states under some force. Okay. and or vice versa. I can charge just the right handed states and not the left handed states. Okay. Let me write that down. One can have a force affecting only the psi-Ls and not the psi-Rs. Is there such a force that we know about? That is exactly the weak force. Remember, we kept saying in the beginning stages of the course that the weak force maximally violates parity, right? I kept saying that if you look at the weak force, the weak interactions in a point mirror, it just vanishes like a vampire, right? So this is where this whole notion comes from, because it turns out that when you write down the weak force before symmetry breaking, the fermions are massless actually. Okay, we will see how to get mass, that is a different question. Okay, the fermions are massless, and so it is completely okay to charge the left handed spinors and not charge the right handed spinors under some force, under some gauge group, and that is exactly the route that nature has taken. Okay. Now seen in this light, the fact that nature violates parity in the weak interactions is actually not a mystery, right? It is totally possible, and nature has taken exactly the course that has been allowed, right? Of course, you can argue that why did nature take this course? It is allowed, but then why couldn't nature charge both of them? So in that sense, some psychological discomfort persists, but nevertheless you see that it is completely natural also that you can violate parity maximally, because you can just charge one representation of the Lorentz group. Why should you charge every representation, right? Good. So I will wrap up here, and then in the next class we will see how more symmetries such as gauge invariances help us in constructing the standard model. Okay. So thank you, see you in the next class.